Stars are hot balls of hydrogen and helium that have nuclear fusion generating energy in their cores. Gas is a compressible fluid and gravity tries to squeeze a star into a smaller, denser volume. However, radiation pressure from the fusion processes occurring in the core create an outward radiation pressure that balances the inward force of gravity. This balance is called hydrostatic equilibrium. This equilibrium condition is very stable over the lifespan of the star. The Sun, our nearest star, contains basically all the mass of the solar system. It is 1,000 times more massive than all the planets, moons and small bodies combined. Its diameter is over 100 times the size of Earth's, and it has an output power of 400 trillion watts. That the Sun was a star was supported by observations made by the Vatican astronomer Angelo Secchi in the 1860s. He did this by using the fairly new science of spectroscopy to compare the Sun's spectrum with that of other stars. When he did, he recognized similarities in their composition. The composition of the Sun, by mass, is 71% hydrogen, 27% helium, and trace amounts of other, heavier compounds, such as oxygen, carbon and iron. The metallicity of a star, or interstellar medium, is a measure of the relative amount of elements other than hydrogen and helium that are present. The Sun is considered a fairly high metallicity star. The Sun doesn't currently make anything but helium in its core. Its heavier elements must have been made by previous generations of stars, and those elements became part of the mix of gas and dust that later formed the Sun and solar system. As one goes from the core to the visible surface, the pressure, density and temperature go down. The temperature goes from 15 million Kelvin in the core to only 6,000 Kelvin at the surface. The core is where nuclear fusion takes place, generating energy and radiation. The core comprises about a quarter of the Sun's radius. The radiative zone is where energy is transported upward by radiation. It is the outward pressure in this zone that holds back gravity. The photons emitted by fusion are gamma-ray photons. Because of the high density of the deep interior of the Sun, a photon scatters 1,000,000 trillion times, on average, before reaching the surface. As a photon scatters off a particle, that particle recoils, gaining some kinetic energy. Meanwhile, the photon loses energy and thus has a slightly longer wavelength as a consequence. By the time it reaches the surface, perhaps some 10 million years later, it likely has the wavelength of a photon in the visible part of the spectrum. Above the radiative zone is the convective zone. As gas cools, it becomes less transparent to radiation. In the convective zone, the cooler gas is less transparent to radiation from the radiative zone. This, and the fact that the temperature of this zone is hotter at the bottom and cooler at the top, causes gas to convect and carry energy to the surface. The photosphere is the thin visible surface of the Sun. Features, like sunspots, can be seen in the photosphere. Also seen in the photosphere are the ends of the convection rolls from the convective zone. The convection is like a pot of water boiling on a small burner, as shown. These granules give the surface the appearance of a boiling landscape where hot plasma rises in the middle of each granule and then descends around the edge. They average around 1,000 kilometers in diameter. The chromosphere might be considered the lowest layer of the Sun's atmosphere. Solar weather, prominences, flares, etc. well up in this region, kind of like Earth's weather welling up in its troposphere. Up until now, the temperature decreased going from the core to the photosphere. Ascending through the chromosphere, the temperature starts to rise again to temperatures between 10,000 to 100,000 Kelvin. Shown is an image of the chromosphere. Magnetic fields cause spicules of gas rise up, like an old 70s shag carpet. Large solar prominences, arcs of suspended plasma, ionized gas, also appear. The corona is the outer atmosphere of the Sun, extending 1,000,000 miles into space. The temperature in the corona soars to 1,000,000 Kelvin. Particles moving at or greater than the escape velocity travel out into space, gravitationally free of the Sun, forming a gusty solar wind. These particles travel at about 1,000,000 miles per hour. Though the light from the Sun only takes 8 minutes to get to Earth, it takes days for the solar wind particles to reach us. The Sun emits about 6.7 billion tons of solar wind particles every hour. Magnetic field activity near the Sun's surface is believed to be the underlying cause of solar activity, as well as sunspots. Rapidly changing fields in the corona accelerate charged particles around to higher average speeds. This means those particles are moving with greater average kinetic energy, which means higher temperature. Solar activity increases and decreases with about an 11-year cycle. The Sun rotates differentially. It rotates with a 25-day rotation period at the equator and about a 30 to 35-day rotation period at its poles. This rotation stretches and contorts the Sun's magnetic field into complex patterns that can give rise to sunspots, flares, prominences, and coronal mass ejections that can hurl an amount of mass equivalent that of a mountain into the solar system. Magnetic field lines can poke up through the photosphere, causing sunspots. These places where the magnetic field has disrupted the convective flow of plasma to the surface, causing it to be over 1,000 degrees cooler at the surface. Ironically, in the atmosphere above sunspots, temperatures can soar to millions of Kelvin, emitting ultraviolet radiation and X-rays. At solar maximum, the Sun reaches a peak of solar activity, then the magnetic fields begin to unwind and solar activity diminishes. The Sun then gradually goes quiet, with perhaps only a few tiny sunspots, coming to solar minimum, completing its 11-year cycle.